Imagine if you could catch a lightning bolt in your hand, would you dare? Now that's a thought, isn't it? When we think of lightning, we often picture a dazzling spectacle in the sky, a testament to nature's raw power. But how powerful is a lightning bolt, really? Well, let's put it into perspective. Picture the energy required to power an average home for a month. Multiply that by around 1,000. That's roughly the amount of energy contained in a single bolt of lightning. It's an enormous amount, isn't it? In terms of raw energy, it's about 300 million volts. That's the equivalent of nearly 75 million AA batteries. And that's just one bolt. During a thunderstorm, hundreds of bolts can strike, each one a powerhouse of energy. So the question isn't just about catching a lightning bolt, but rather, so how can we possibly think of catching such a massive display of nature's power? Lightning is more than just a bright flash in the sky, it's a complex scientific phenomenon. It's a spectacle of nature that occurs when imbalances in electrical charges within our atmosphere reach a tipping point. But what exactly triggers this dazzling display? To understand this, we need to dive into the heart of a storm cloud. Inside these towering formations, minute particles of ice and supercooled water are constantly colliding and bouncing off each other. This seemingly mundane activity sets the stage for something far more dramatic. Through these collisions, smaller, lighter particles gain a positive charge and are swept towards the top of the cloud, while the heavier, negatively charged particles sink to the bottom. This separation of charges creates an electric field within the cloud. Now, our planet isn't just a passive observer in this process. The Earth's surface is positively charged, and it's this contrast between the negative charge at the bottom of the cloud and the positive charge on the ground that leads to the spectacle we know as lightning. When the electrical tension between the ground and the cloud becomes too great, a channel of ionized air, or leader, begins to form. This leader zigzags its way down towards the ground in a series of steps, each around 50 yards long, at a speed of roughly 200,000 miles per hour. Simultaneously, an upward leader reaches up from the ground, and when these two leaders meet, a pathway is established for the electric current to flow. This is when we see a lightning bolt. It's an intense release of energy that heats the surrounding air to around 50,000 degrees Fahrenheit, which is about 5 times hotter than the surface of the sun. This rapid heating and cooling of the air generates a shock wave, which we hear as thunder. So, lightning is not just a beautiful natural light show, it's a powerful display of electrical energy in action. Understanding the science of lightning is the first step towards imagining how we might harness its power. Harnessing the energy of lightning is a concept often seen in science fiction, but what about reality? In the realm of reality, the idea of capturing lightning's raw power is, well, electrifying, but it's also riddled with challenges. First off, lightning is unpredictable. It's like a wild animal, striking where and when it pleases. Scientists can't predict exactly when or where a bolt will hit, making it difficult to position equipment to capture the energy. Not to mention, the sheer force of a lightning bolt could easily destroy any unfortified equipment in its path. Secondly, the amount of energy released by a lightning bolt is immense, but it's released in a flash, literally. A typical lightning bolt unleashes around 5 billion joules of energy in just a few milliseconds. That's enough energy to power an average American household for about 6 days. But harnessing all that energy in such a short time is a monumental task. Over the years, there have been attempts to tackle this electrifying challenge. Benjamin Franklin, with his famous kite experiment, was one of the first to attempt to understand and harness lightning. Today, researchers are exploring more sophisticated methods. For example, some scientists are studying the use of lasers to create a path for the lightning to follow, allowing it to be directed to a specific location. However, these attempts are still in the experimental stages. Then there's the issue of storage. Even if we could capture a lightning bolt's energy, storing it for later use is another hurdle. Current battery technology is not capable of absorbing such a massive amount of energy in such a short time. Despite these obstacles, the idea of harnessing lightning's power is not completely off the table. With advancements in technology, who knows what the future holds? Could we one day build a lightning farm where bolts are harvested like crops? It sounds like a scene from a science fiction novel, but in the world of science, fiction often becomes reality. Though we have yet to successfully harness lightning's power, the idea continues to captivate scientists and dreamers alike. While the idea of capturing lightning is fascinating, it comes with significant risks. The sheer power and unpredictability of lightning make it a dangerous entity to try and harness. First and foremost, there's the potential for injury or even death. A single bolt of lightning can carry over 1 billion volts of electricity, That's enough to instantly fry any living thing in its path. Then there's the challenge of containment. Imagine trying to hold a wild stallion with a piece of string. You're essentially dealing with the same problem when it comes to capturing lightning. It's a force of nature that doesn't like to be confined. Safety measures and precautions are paramount. Protective gear, insulated environments, and a deep understanding of meteorology and electricity are just a few of the necessities. Despite these challenges, the pursuit of harnessing lightning continues, driven by the potential benefits it could bring to our energy needs. The endeavor to catch a lightning bolt is not for the faint-hearted. If we were successful in capturing a lightning bolt, could it power the Earth? A fascinating thought, isn't it? Each bolt of lightning carries about 5 billion joules of energy. Sounds a lot, right? But in reality, that's the equivalent energy used by an average American home in roughly half a day. This means to power a single home for a full day, we would need to capture 2 lightning bolts. Now scale that up to powering the entire Earth. We're talking about millions, if not billions, of lightning bolts every single day. While the idea is intriguing, the feasibility of capturing and storing this energy is a significant challenge, not to mention the inherent unpredictability and dangers of lightning. The dream of powering the Earth with lightning is a lofty one, but as we've seen, nature's power is nothing short of astonishing.
Don't forget to like, subscribe, and share this video. That's all for Nifty Narration.